Let's get started with a simple example, and that is maybe just a network like this one, where we have 4 different nodes connected with each other, talking with each other. Why is that working? That is working because they are talking with the so-called Ethereum protocol. So if you start a blockchain node, and if it's connecting to another blockchain node, or if you start a blockchain node and you're trying to connect from outside an RPC interface, that is a standard protocol on both ends. So the nodes know how to talk with each other, and there are different nodes who can talk with each other. It's not just one software that is called the Ethereum software. There's different implementations of the same protocol in different languages. So for example, Go Ethereum is one blockchain node. Parity is another implementation of a blockchain node. Then the new Hyperledger Bezo is another implementation of a blockchain node. And they are all talking the Ethereum protocol. So they know how to talk with each other. Okay, so we have these 4 nodes, they talk to each other, and they form a so-called blockchain network. And it doesn't mean that you have, with any Ethereum node, you have to connect to the same network. You can just use Ethereum within a consortium or in a private network. So you can have a totally separate network, which is talking the same Ethereum protocol, but differently separated from the main network. And that would look like this, where you have a main network on the one side and a private network or a consortium network on the other side. And in terms of data, it also means that they both do not contain the same data, especially if you start them from scratch. If you start your own network from scratch, then you have a totally different data set. You send off a transaction to the network and to the private network, then it's only registered in the private network. And since it was never connected to the main network, the data is totally, entirely different. That could be suitable for banks or for governments or anywhere where data privacy is not only recommended, but a requirement. But you can also have partly the same data as on the main network. This happens when you fork the main network at some specific point in time. You take the existing data of the main network and you just continue with your own private network from there on. That means all the transactions that happened until this point, where we have this blue, they should represent blocks here, and you start to fork this main network at this point, then all the blocks until the fork are the same as on the main network, and after that in your private network they will be different. So this could be one potential scenario. Anyway, however you start your private network, it usually starts with, if you start your own private network, it starts with a Genesis block. This is the first block that is written to the network, and it usually comes from a Genesis file, and that Genesis file is the configuration for your Genesis block, and from there on all the blocks build upon this first block. So this is the only thing that you have to configure when you start your private network, and we're going to do this in later sections of this course after the Solidity introduction. All right, let me just compare a couple of things. First of all, we have the main network, and the main network is the network where ethers cost money. It is also the longest existing network, and it's the network where seldom data is changing. So in terms of they are not introducing a lot of changes to the underlying protocol. And then we have different other networks, and we have already worked a little bit on Ropsten. There's also Rinkeby, there's Kovan, there's Goerli network, and there are a ton of other networks. They are similar to the main network, if not exactly the same, just with different underlying data, and they are here for testing. They're here for testing consensus protocols, they're here for testing different other protocol changes, they are here for giving developers, especially smart contract developers, the ability to test certain things on the network. And they all still require mining. So when you deploy your smart contract, or when you send off transactions to any of those networks, then you will need for the transaction to be mined. You need to wait for the transaction to be mined. So this is why at some point, and actually very early on, developers, smart contract developers, started to implement their own blockchain simulation. That was first the Ethereum JS Test RPC, and then it was called Ganache, and is now part of the Truffle suite. And also, if you just work in Remix, then we were working with the JavaScript virtual machine, which is just an in-memory implementation. Usually with these developer networks, they are fairly similar to real networks. There are a couple of differences, not only the speed, but also you will see it later, for example, in the JavaScript virtual machine, you can have return values from transactions, and in the real network you cannot, and I will tell you exactly how you can get around this. But if you are testing on Ganache, then at least before you go into production, and that is very important, you should test it also on real networks. And we will see that later with unit testing and so on. So definitely stay tuned in this course. So let me wrap it up a little bit. The main network, on the main network, when you send off transactions and they are getting mined and data is persistent, so any transactions that are getting mined in blocks, they are immutable. You cannot take them back anymore. It's a real blockchain, and on the main network, obviously, the ethers, they cost real money because we agreed upon it. There's a demand for it, and they will also most likely not go away. I think the Ethereum network had an uptime of 100% in the last 5 years. So I think that's a fairly good uptime, and it's very robust. Then we have test networks such as Ropsten, Rinkeby, Goerli, or Kovan. Data there is persistent, but from time to time, where there is no guarantee that it's not going to be deleted by tomorrow, it is a real blockchain. Especially Ropsten is a clone of the main network, where you can get test ether, see if your smart contracts are working, see if you can onboard beta users, and you can just work from MetaMask, for example, directly with those test networks. It's there for beta releases and so on. And then we have developer networks like Ganache, or well, actually, let's keep it with Ganache. It's there for unit testing. It's very fast. You've seen that transactions are mined immediately, but data is usually not persistent, and it's not exactly the same as a real network, but it's fairly similar, and it's perfect for testing. Now, what are the key takeaways from this lecture? First of all the nodes are talking the same protocol. That is the Ethereum protocol, and that is important to understand because for all the nodes, it's the same way of storing data. It's the same way of accessing those data. It's the same way of creating those blocks. So when you start your private network, a consortium network, or when you connect to the real network, you always speak the same protocol. You have the same tooling, you have the same programming language, you have the same underlying libraries. So that is very important to understand. Then there is the live network. On the live network, the ethers cost real money, data is persistent, and it's probably going to stay there forever, or at least until the last miner or the last node left the network. I guess that shouldn't happen so quickly. Then there are the test networks. The test networks are here to actually test your smart contracts, do onboarding of beta users, the protocol developers that test protocol updates there, or node developers test their blockchain nodes, so nothing can go wrong. And then we have the developer networks or your private